Okay, let's start talking about the voltage regulation control. Since we already learned some methods used for frequency regulation control, we're going to take almost the same approach to model the control system for voltage with generator, but there's some new elements different from frequency regulation because frequency regulation is mainly done by generators. Only in emergency conditions, you may need to do some control on the low side, like load shedding. But for voltage control, it's a little bit different. So we will explain what difference the voltage regulation has. So some part of control will be done not by generator, by some other compensators or voltage controllers. So we're going to cover the control with generator and control not done by generator. So we'll utilize some materials from those three books. Okay, let's first talk about how reactive power is transferred from one location to another location if we consider a single transmission line. So if we draw the phasor diagram about the voltage phasors of both ends, and here we assume no resistance on this tie line. To calculate the active power from the left to the right, it will be very simple, just product of the magnitudes of two voltage phasors divided by the reactance and then multiplied by sin delta. Okay, so this is the active power sent from the left-hand side. And the active power received from the right-hand side is exactly the same if we ignore any resistance. So if we want to increase active power, we can just increase the delta or decrease delta to decrease active power. So delta will be critical for changing the active power. Okay, but to calculate the reactive power from a left-hand side, it will be this formula. I don't go to the details on how to prove this one. It's pretty simple. You just start from the definition of compressed power, and using the phasor diagram, you can take the imaginary part, so that would be the QS. So here, if delta is small, and usually we can utilize this formula to estimate how the reactive power can change with the system. So here, the main change on reactive power depend on the voltage gradient from the left-hand side to the right-hand side, which means if you want to make a QS to be positive, ES need to be higher than ER. And if you want to increase Q, and ES should be increased, right? We need to increase the difference between the voltages on both ends. When we calculate reactive power, it doesn't give you a symmetric form of the formula, but it's not opposite of the reactive power sent from left-hand side, because even we consider a lossless line, it doesn't mean the reactance is also zero. It still has some reactance. So this reactance itself will consume some reactive power. So the difference will be reactive loss on the line. So similarly, but you still need to increase the gap between the voltages on both ends to increase either the reactive power sent from the left terminal or the reactive power received from the right terminal. So the loss of the Q or reactive power will be basically just reactance multiplied by the current magnitude square. So because current will depend on the P and Q and the voltage. So if you see, if you increase Q, if you increase the reactive power delivered through the transmission line, this loss will also increase. So the byproduct of increasing the reactive power delivery will be increase of the reactive loss. If we also consider the resistance of line, this will be active power loss. Similarly, if you increase either P or Q, that will increase the loss of the active power. Okay. So from this simple example, we know the voltages are very different everywhere. It's not like a frequency. So under steady state condition, all everything in the entire system will have about the same frequency. But in the power network, because we have power flow, the power flow will include active power and ready power. In order to have ready power flow, you need to have the gap. So this one cannot never be zero, right? So you will have difference of voltages between any two neighboring substation. So if you want to deliver ready power from one point to another point, you will intentionally create such a voltage gradient to determine where the power flow will go. So here we have two conclusions. The first one is ready power flows from a high voltage to low voltage, but cannot be transmitted over long distances because it requires very large voltage gradient. So if you want to intentionally deliver ready power from one point to another point, and based on this formula, you can calculate how large voltage gradient you're going to generate, okay? Divided by the radiance, the total radiance along the path. You need to make that answer to be same as your target, okay? But if that turned out to be the ES will be much higher than ER, that's not reliable, because when you change all the voltages into per unit value, all the voltages will be even they can be different, but it will stay very close around one. For instance, for transmission systems, usually engineers expect to have a positive or negative 5% variation of voltage for high voltage line. For even higher, like actual high voltage transmission line, they expect to have the variation to be very small. Okay, not as small as frequency deviation, but it's still very small. Let's say 5%. For a distribution system, that 5% may increase to 8% or even 10% in some area, but it's still pretty small. So which means this gap at the most will give you about 10%, 5 to 10% difference, okay? And divided by the total radiance, there's a very limited ready power you can transfer from one point to another point. So you have to utilize some other methods, not just generator. You cannot use generator to deliver ready power to the entire network. Another conclusion is it's also not very economical to deliver a large amount of ready power, because that will increase current and increase loss of both P and Q. So this is the something make a ready power and voltage control different from frequency control. So the primary objective of voltage control is definitely to ensure the safety or the healthy condition for equipment, because any electric equipment, when they connect, when it is connected to the network, it will have some voltages they can operate in order to avoid damage. So we have to make sure at each connecting point of such a equipment, the voltage can vary within very narrow range to avoid any damage. The second objective is to make sure the voltage of the entire system has good profiles, such as, for instance, if you can make all the voltage to be close to 100%, 1 per unit, the nominal value, which means you can safely deliver active power through the entire network. Because if we only take a look at this equation to determine how the active power is delivered, we want to make sure those both voltage are high enough, right? So if you think about in the power system, you have short circuit, and that lasts for a long time to make voltage close to zero, which means the active power cannot deliver beyond that point. Because when you get to that point, this answer will be close to zero. So it's like you create either a wall or some black hole, so that the power cannot go to pass that point. So if you can make sure voltage everywhere will stay at about 100% of their expected value, which means you can safely deliver active power to any location. So that's secondary objective of voltage control. The third objective will be the transmission efficiency. If you can design how the ready power is dispatched and is provided within the network, you can minimize the current along some long transmission lines, and such as you can reduce the transmission loss. So the first method to control voltage will be using the excitation control system through a controller which is called automatic voltage regulator, or VAR, which is similar to the governor of the generator for frequency regulation. So it will perform a droop control to try to maintain the voltage at either terminal or maybe a remote location near the reference value. Because you cannot deliver a rated power over long distances, you also need to put some local control devices near the load where the equipment is far from any generation. So you need to utilize a local controller to maintain the voltages. Such controllers include VAR sources or sink. Sources means they can provide additional VAR to increase voltage. Sinks means they can absorb additional VAR, extra VAR to mitigate high voltage, such as shunt capacitors, shunt reactors, synchronous condenser. Synchronous condenser basically just a synchronous motor or synchronous machine, not generating any active power. Static VAR compensators and static synchronous compensator, stay calm. So we'll talk all of them later. There are also some line reactance compensators such as series capacitors. They also can contribute some of reactive power. A transformer is also another important component in the voltage control. Okay, so let's first talk about the excitation system of a generator. We know this equivalent circuit for in D axis. I didn't draw a Q axis circuit because the exciter is actually stay within only D axis, right? So we have this actually the source of the field current. Field current is a DC current. So this one is the DC source. So it will provide this field current, and the field current will provide the electromotive force, right, as an internal source. So later in our circuit, you can model that one either by the capital EQ for static condition, or maybe E single prime or E double prime, or just for the transient or subtransient dynamic. But they all depend on the field current. The field current is flowing in the winding of a rotor, so the current going to the external system for this circuit will be ID. ID is just real part of the terminal current. So if you take a look at any single phase, so you can use I terminal IT for the terminal current going to the system. So the primary function of the excitation system is to provide a direct current to the field winding of the synchronous generator. Additionally, the automatic voltage regulator, or AVR, with the excitation system performs control and protective functions essential for the reliable operation of a power system by regulating the field voltage and consequently the field current. Under steady state condition, the system should supply and automatically adjust the field current to maintain terminal voltage as the output varies continuously within the generator capacity. During disturbance, the excitation system will be very critical because it needs to respond to the transient events with the field forcing consistent with generator instantaneous and short-term capacity. When we move to the stability sections, then we'll introduce some cases in which we need a excitation system to enhance the stability of the system. So actually, the very simple reason why the excitation control system is very critical for stability is we still need to go back to this formula. Although this formula describes how the power delivered from one end to another end of a transmission line, but it also applies to the power delivered from inside of generator to the system, right? Because if you treat the generator as one end, system at the other end, if you increase the excitation system, increase the field voltage, that will increase, for this case, will be the ES. That actually increase the power you can deliver to the system from generator. That's very critical, because if there's a short circuit near the generator, that will make the ER be lower. That actually reduce IT power. Think about the power balance between the mechanical power and the electric power, because if that power is unbalanced, the rotor will be speed up based on the Newton's second law. So when the ER decrease, if you're able to increase ES, you can compensate that change on that IT power. So you can still continuously deliver about the same amount of IT power. That's very critical. So when we go to the transient stability section, we'll discuss on the role of the excitation system. So in this slides, I highlight two currents. One is a field current, the other is terminal currents. Keep in mind, any generator is not ideal, which means no matter what circuit is carrying that current, that circuit always has some resistance. So resistance will generate some heat. Okay, so when either of those two currents are not too high, there's no concern. But if the current is become higher, like for instance, and there's some disturbance, you want to increase the field current, that will increase the heat generated on that circuit. If it operated over a long time, that can burn or damage that circuit. So any current need to have some limit. So that limit actually determines the controllability of the generator. So go back to this voltage control. So if the current becomes smaller, the rated power capacity of the generator also become reduced. So we need to consider the heating limit for both the terminal current and the field current. So that will come with this figure, which is called the D curve or D chart of a generator. So this chart describes the first quadrant and the fourth quadrant of a generator operation. So X is P, Y is Q. So because it's about generator, so we assume the P is always positive, and the Q can be positive or negative, which means while the generator is generating active power, it can either provide reactive power or consume reactive power. Okay, so that will determine whether you operate in the top, which is over excited condition, or bottom under excited condition. And this boundary is like a D, letter D. That is the boundary of the generator. So you're safe to operate within this boundary. So if you operate at 100% of voltage, so that will be the green boundary. If you can increase the voltage without changing the current, and that will give you more power, so it can become the blue boundary. But anyway, there's such a boundary. You have to make sure not going outside of the boundary. So how to prove or derive such a curve? We can start from this equivalent circuit. The generator has an internal voltage source, EQ. So usually we know the EQ is roughly proportional to the field current. Okay, and we can draw this phasor diagram. And this phasor indicates the internal voltage phasor, right? That's proportional to the field current. So if I ask what are the P and Q delivered to the external system from the generator, we can use the terminal quantity, right? Based on the power factor, we can easily know P will be their product with power factor, cosine phi, and the Q will be the parent power multiplied by sin phi. So here you see the both formulas have the terminal current in it. And we can also derive the the formula to calculate P and Q using the element inside of this circuit by using the internal voltage. So just make a formula simpler, and we just ignore R, which is the resistance of armature winding. Okay, so you see, this is basically the same formula from the previous slides about how the IT power deliver from one point to another point. And this is the formula for reactive power. Both sides of formula can give you same answer and P and Q. But why do we need to see the both sides of formula? Because first side involve the current of a terminal, second side involve current of the field winding. Then we can set up the limit for each current and then decide what is the maximum P and Q for the generator to operate if we consider such a limit. So we already know the answer has to be that the D curve. Okay. For generator, if we assume, we always assume P to be positive. For the Q, if it's positive, we call it over a static condition. If it's negative, we call it under a static condition. If we consider both limits for the terminal current and for the field current, we actually can draw two circles, because if you're familiar with the form of the two sides of formula, each side of formula is actually it's describing a circle in the polar coordinates, right? Because phi will be the variable to change. And this product, which is the apparent power, will be constant. So that actually indicates the radius of the circle. So that is actually this radius. And for the second set of formulas, that's also a circle, but that will shift the radius, the center of the circle down to this point. This point will be determined by this value. So basically, there are two circles. One circle based on the terminal current will have this radius. Second circle based on the field current will have this radius. So that determines the two parts of the boundary. Definitely, if you continue drawing that orange arc and to finish the circle, that give you basically the same as D chart. Actually, in this figure, that is about that case. But in some generators, we also don't want the generator to operate in under a static condition for a long time. So you can add another part of the limit as the dotted line shown there, or you can just give further protection, so that will cut one part of this this area on the bottom, but it will finally give you about this D curve. Okay. So this give you an idea on how to determine the limit of P and Q of a generator, and this is critical when you study voltage stability, because when you study voltage stability, you need to check for any condition the generator already go outside of this boundary. So for instance, if we go outside from this direction, that will violate the current limit of the field winding. So the field winding limit will react. Okay, so either try to stop the current only at that value, it may trip the units. If it stop at that value, which means the Q cannot increase further, it will stop there. If the unit is tripped, you're going to lose this VAR source, because the generator is also VAR source. You have even worse voltage, right? So for like if you have your operator, you're dispatching the system. If you dispatch P too much, and that comes with high Q, and you expect the generator to give you that Q, but it's already outside of this curve, that generator is tripped, and you lose that both P and Q from that generator. That can be very bad. So next we can start modeling the control loop of the voltage for generator, and we show this figure earlier, and we have discussed the modeling for another control loop for the frequency regulation, which is low frequency control. But now we are going to focus on the voltage control part. So that voltage control loop will have a number of components. We're going to model each of them. So the center is a generator, and this exciter will determine the field current. And before that, there's a regulator to decide the control signal to the exciter. And there's also other component to measure the terminal voltage and send it back, like this one, the terminal voltage transducer and the load compensator. They try to measure the voltage signal or other signal back, give it to the regulator. And we also have a reference. So that actually finish the closed loop. For the safety of this equipment, you can also add like a limiters or protective circuit related to terminal current or field current. And there's another component. We'll discuss this component in the section of a small signal stability. This one just to provide additional damping to the generator. Exciter, regulator. Regulator is basically the AVR. And terminal voltage transducer and the load compensator and power system stabilizer. So we'll cover all of them. Okay, last will be the limiter and the protective circuit. And we don't go into the detail, but basically they try to protect any circuit in case they reach the limit of the current. Okay, so let's model this control system. At the terminal, in order to measure voltage at terminal, so you have to use some potential transformer. Potential transformer is just one type of sensor. It just gave you a low voltage signal proportional to the actual high voltage at terminal. But this voltage will be a three-phase voltage. In order to convert this three-phase voltage into the DC voltage, you have to use a rectifier. The rectifier will give you still voltage signal, but which is DC, and you can give it to your control system, okay, as a feedback. Oh, so here there are also stabilizers. This stabilizer is not a power system stabilizer; it's just internal stabilizer to increase the stability of this excitation system. So if we model this control system, okay, and we have a reference value voltage. This reference voltage will be what we expect for this voltage to be. If this voltage means terminal voltage, and reference voltage will be the terminal voltage. And the sensor will measure terminal voltage and give it back to be compared with the reference. So we use a first order system to model sensor, because sensor has to be very fast and very sensitive. So we can imagine the time constant here is very, very small. KR will basically just translate the unit from terminal voltage to the reference value. So if a terminal voltage represents the true voltage of the generator, it can be very high. And if you take the same unit as the reference voltage, so this KR can be 1 if they take the same unit. So amplifier will determine the gain. Basically, the most important part will be this Ka, will determine the control gain. This is a troop control. So it won't be able to give you won't be able to eliminate the difference between the terminal voltage and the reference voltage. So which means this one will never be 0. Oh, sorry, not this one. I mean, the difference will never be 0, the error signal. This one will be always 0. Will always never be 0. Okay, so then this signal will be amplified through the amplifier and then become control signal going to exciter. Exciter will determine the field voltage. Field voltage goes to the generator. So here the generator is modeled by first order system, and they'll become the terminal voltage. So now you should be able to write down the transfer function. So if we know, let's take a look at the range of values for those time constant or gains. So TR is the time constant for the sensor. It has to be very fast. So usually the time constant is like a millisecond time frame. So like from 0.01 to 0.06 second. Amplifier is also very fast, also like 20 millisecond, around tens of millisecond. Exciter is also very fast. Okay, and then the last one will be generator model. Generator model, this KG describe how. So if you change all the voltage in the per unit value, you divide the terminal voltage per unit over the field voltage per unit, that tell the game. So this KG is not some value you can set up. It basically just describe first order linear model for your generator. So based on the first order simplified model of generator, you can determine this KG and also tau G. Tau G will be the time constant. Tau G here usually is 1 second or several seconds. So let me ask the question, what is a tau G? So based on what you have learned in the generator modeling section, we have very detailed model of a synchronous generator, right? We start from the transient, subtransient dynamic and steady state, and we introduce many different time constant EQ and DSs. So what is a tau G? This control loop that only controls voltage. It doesn't control anything about angle, speed, or active power. So it doesn't depend on inertia. Right? This one doesn't include the turbine governor. So you can have an exciter generating the field voltage. The field voltage will induce some terminal voltage. You can replace the rotor by increasing the inertia, decreasing inertia. That doesn't change this circuit, this system at all. So it doesn't depend on the inertia. What is the tau G? We go back to this circuit because this circuit is the most likely related to this system because input will be this field voltage. This field voltage, even I use different notation, but it's actually exactly the delta V capital F in that system. And the output will be the terminal voltage, right? Terminal voltage will basically just. So if we figure out what time constant this DS's network have, so we'll be able to estimate the tau G. Do you know what time constant this one has? Which one? So this is D circuit. It cannot be Q circuit, right? It has to be how many Q circuit time constant do we have? We have a TD0 prime, TD0 double prime, TD prime, TD double prime. So which two are actually on the bottom of the transfer function? The open circuit time constant. Those two. Okay, so we know the TD0 prime is much longer than TD0 double prime. So for simplicity, if we ignore the double prime time constant, so this one will be about the value of your tau G. So that's why the tau G will take 1 second to a few seconds. All right, so this one, it doesn't depend on inertia. So now we can write down the transfer function. So first it is open loop transfer function. Open loop transfer function is very simple. It just calculates a multiplication of all blocks, no matter it's on the forward path or maybe the feedback path. So it's just multiplication of all the 4 blocks. What is the closed loop transfer function? The closed loop transfer function for this system will be the open loop transfer function divided by, the forward, the product of the forward 3 block, the multiplication of those 3, divided by 1 plus the open loop transfer function. And you do some simplification, you will have this one. And because in this control system, if you consider per unit value, every signal anywhere will be voltage. Okay. And if you already take per unit value, so there's no reason to have, for example, KE, KG, or KR be very large or very small. So usually are very close to 1, because you are translating voltage signal to another voltage signal. So only one atom which is not 1, not close to 1, that is Ka. Yeah, this is amplifier. That is the gain of the control system. All right. So if we consider a step input, using the final value theorem, the steady state response will be just let S be 0. So the steady state voltage will be this one. Okay. And if you assume this one is around 1, and those three around 1, so you have this atom. So from this answer, you know it will never be 1. The steady state voltage will be always, after the change, will never go back to the nominal voltage. Only if you have Ka to be infinite. This one can hold to 1, but it's not practical, because that can make the control system be unstable. So there's a similar example to the example we learned from the low frequency control. It's using the exactly same two methods. One is the Ross table, the other is the root locus method. And I don't go into detail, but they take exactly the same procedure to draw the Ross table. And from the table, the first column had to be all positive. So the only conclusion is, for this example, K has to be less than 12.16. So that will be the limit for the gain. You can also draw this using this root locus method. In my lab, it will be very simple. You can, once you provide the transfer function, you can draw each root locus for you. And you will see this locus will intersect with the imaginary axis at the point where the Ka equals 12.16. That's the same limit we found out from the Ross table. Okay, so let's try some values of K. The first one, let's try a very small value for K. And from the steady state voltage, we know the steady state voltage, also here, the steady state voltage will be basically the Ka divided by 1 plus K, right? So if you K is equals 5, that's basically 5 over 6. So the steady state voltage only go back to 83% of the reference voltage. So there's a huge gap. This one definitely cannot be accepted by any system. It's too large. So you have to increase the gain. If you increase to 10, it's still lower than the limit. You see it has a lot of oscillation. And the gap now is about 0.1. It still have more than around 10% of the gap. So that's also not acceptable for most of a transmission power system. If you really increase this gain to the limit, you will have equal amplitude oscillation. The system is operating at a marginally stable condition. And even for this case, you know the final voltage still have large gap from the reference value. Okay, so which means for this system, as long as there's a disturbance, the voltage will never go back to the original value if for a permanent disturbance. So what can we do? For low frequency control, we still have AGC, right? But first of all, for the low frequency control, even without AGC, the frequency can still go back to a value very close to 60 hertz. But for this case, the voltage are very different from the nominal voltage. So we have to add stabilizer. So many excitation systems, they will have integrated stabilizers. Stabilizer just try to improve the stability by allowing a bigger gain. So we know without stabilizer, a bigger gain will cause instability of the control system. But by adding the stabilizer, you can increase the gain, such as you can get closer to the reference value. The simplest idea is to just add another feedback loop. This will be part of the excitation system. So those elements will be part of a excitation system. You simply just add this to a feedback loop. Okay, so here you need to design the gain, the KF, and the tau F. Tau F may be something you cannot design based on what technology you use to implement the control, but you can design. Definitely, you want to make a tau F to be proper for your excitation system, and you can design the KF. For instance, if you find out that example in Sadet's book, and it will give you a MATLAB code or the Simulink file, so you can actually by selecting different value of the K and the tau, and you can apply the same disturbance. For instance, for this case, we still take the gain, which is 10, right? Earlier, this 10 doesn't give you a very good result, but now by adding this stabilizer, you see the curve become much more stable, such as you can further increase this gain and to get closer to 1, which is 100% nominal value. So what this stabilizer does, basically just add a chained open loop transfer function. Does anyone know how to chain the open loop transfer function and to improve the stability of a linear control system? Okay. Yeah, it should be covered by linear system control. Like for this case, so that's the original open loop transfer function, right? So it has the 4 time constant. So each time constant determine a open loop pulse. So which is drawn here. Those 4 poles together determine those each individual root locus. Okay. So we pay attention to the root locus that can intersect with the imaginary axis, for example, this one or that one. We don't worry about anything else. The others may change the time performance, but it doesn't change the stability of this system. So only just identify those 2. So now we know for this system, if the gain is around 12, the system is going to lose stability and beyond that value. So what you can do is you can add another pole. Once you add another pole, each root locus will shift. They still follow the, there's a number of formula which we tell. So how, if I give you the location of the open loop transfer functions poles, how do you roughly draw each root locus, right? So those rules can still be applied. So that will change the angle and direction. So for instance, if you add additional pole, that can make this root locus more pointing to different direction. So that gives you additional room by using even bigger gain without losing stability. Okay, I don't go into further details, but I suggest you can, because this Simulink model and the model with stabilizer provided by the textbook. So you can play with those 2 files by setting different value. There's a possibility if you properly select that new pole, you can make the root locus be further from the imaginary axis. So that will give you more stability margin, but you need to select proper value. It doesn't mean any value for tau and k will give you a better stability. Definitely another way is you just add a PID controller, right? PID controller, even if you use a smaller gain, it can still guarantee to go back to the setting point. This is also an option, but it will be more complex than the first example. So for this case, the voltage will go back to the reference value. The Simulink file is also provided in the book. Any question? Okay, so next we need to explain one thing. We left this question from the generator modeling session. If you remember, there's one very busy slide, and we start from a flux linkage equation, voltage equation, gradually derive finally a set of differential equation, only using the time constant and IC single prime, IC double prime. And there's one step I didn't use this EFD. EFD is a field voltage. I use something like a capital EFD. I said using this capital EFD will make the entire equation somehow simpler, and which is actually the conventional way to model the generators with exciter. So I'm going to explain why do we need to do such translation. Okay, so earlier all our per unit system is based on the LAD based per unit system, and actually rigorously speaking, this one is called a reciprocal per unit system. What it means is if you define the base of current and the base of voltage, you automatically determine the base of impedance, and also automatically determine base of admittance. So which means if there's an independent, if it's not independent variables, its base value can be determined based on others. Okay, but that will give you some something which is not very convenient, especially when you deal with exciters modeling. So one example is, so if you follow this per unit system, the armature terminal voltage ET is basically around 1, okay, under normal condition. But in that differential equation for the generator, the exciter output voltage, the lowercase EFD will be very small, will be 0.001 per unit. You may think that's not a big deal, right? You can just multiply this one, divide or multiply this one by some number. But when you simulate a lot of generator using computer, each computer has some precision level, which means when you get close to that level, the generator will have increased error. The accuracy will decrease. You want to deal with all the computation staying away from that precision level. For example, I don't know today's computer, if you use MATLAB, the precision level will be maybe 10 to the negative 16 or 24 or 32, I don't know, but there's very small number, okay? But you deal with a lot of generator variable, and their actual value in the per unit is very small. That actually increase error for the each numerical step. So you want to translate every variable, the values, into a range which is near 1. So that will be ideal. For instance, if we go back to that example in that same generator we calculated before. Okay, so taking that value, the EFD will be 0.000939. Okay, that's very small. Then we want to take an alternative, which is somehow like a reciprocal per unit system. So we expect for 1 per unit field voltage, so this capital EFD is a proportional to lowercase EFD, but it's amplified. So this value will stay around 1, okay? And there's another 1 per unit field current. That one is also stay around 1, but that's proportional to the lowercase FD. So how do we determine the new basis for the capital EFD and IFD? So if the voltage, terminal voltage around 1, and usually the field current will be around this value, and the field voltage will be around this value. So based on that example, we already know, so the EFD can be very small. IFD seem to be okay, right? But EFD is very small. So it's very naturally to assume the capital IFD, just the lowercase fd multiplied by LAD. Why? Because from here, so you easily know, so 1 will be around LAD multiplied by IFD. So if we multiply the IFD by that indulgence, so the capital IFD will be around 1. Similarly, from the second equation, we know if we multiply the EFD by this factor, so that capital EFD will be around 1. So for instance, if you do the calculation, so the capital IFD, EFD will be higher than 1. Okay, although they're not near 1, but they're much better than very small number. So usually in any model, sound exciter, it doesn't use the lowercase EFD or IFD. They use the uppercase EFD and IFD. But there's some internal translation using those two formulas. Okay, so you only just need to be aware of this one. You don't need to you don't need to memorize this one, or unless you want to program the simulator for power system to model everything. But when you take a look at the manual of software and deal with some data, just keep in mind, in most of existing models, they use capital EFD for the voltage. All right, so next we can create the entire the block diagram for the automatic voltage regulators, including the exciter and generator. This is just the structure of detailed excitation system. So for instance, this is the field voltage is going to, is capital EFD, is going to change the field voltage of the generator. So the generator is just outside of this box. This part will be the exciter model. It can be more detailed model. And then before that one, those will indicate some of the amplifier model. And it has multiple loop, just improve the stability. It can have maybe 2 minor loop stabilization or major loop stabilization. Just try to add more open loop holes, right? By adjusting those open loop holes, you can have better performance. The input of this control system will be the setting point. This is the voltage you expect to have for the terminal bus, so maybe the location you want to control. And there's another, so what signal is missing? The missing is the feedback signal of the terminal voltage. So this VC will be the feedback signal of the terminal voltage or the controlled voltage. This other signal may be from the power system stabilizer. So we'll discuss this one in the next session. All right, so VC come from another system. Okay, so first is this time constant TR. The TR is the same as the sensor we discussed earlier. This is just to model how quickly you can collect the voltage data and give it to the feedback of this automatic voltage regulator. The TR can be very small, which is just same as TOR earlier. It's called the voltage transducer. And on this side, you measure terminal voltage as well as terminal current. Okay, so if you only measure terminal voltage, you give this signal directly to this transducer, you're going to only control the terminal voltage. So why do we add another more complex block, which is a load compensator? We just gave the AVR additional capability to control remote voltage, not just a local terminal voltage. So how do we do that? Which we measure both terminal voltage and terminal current. And using this formula, we can calculate another voltage value. And we are going to control this value instead of terminal voltage directly. And RC and IC are both parameters you can set up. If you make RC and XC both be 0, what is VC? VC will be terminal voltage, right? So if you make RC and IC both be 0, so this one will be terminal voltage, the magnitude of terminal voltage. If it's non-zero, this VC will be different from terminal voltage. Okay, you can even imagine, what if I take both XC and RC be positive? Those two are some value I can take arbitrarily. If I make a RC, IC both be positive, my question is, the magnitude of VC is bigger than ET or shorter? It's bigger or smaller? Do you know that? Can you make a guess? So if I make a RC and IC be positive value, real number, any number, as long as they are not 0, the VC will be different from terminal voltage. That voltage will be higher or lower than the terminal voltage. Yeah, we can. So this is just detail, but let's talk about same story. Let's, if you don't look at the answer, just use this phasor diagram. So this phasor diagram is describing how you have terminal voltage from the internal EMF EQ. So internal, the EQ is much longer than ET, right? For this case, this is terminal current, IT terminal current, and ET terminal voltage. That's the same IT, ET there. And here, the red is SQ or resistance RA are both positive. So when you have both positive R and positive X, that make EQ be longer. So for instance, in that formula, if you make RC be exactly RA, XC be exactly XQ, what happened? VC will be EQ. All right. So you're actually controlling that EQ. Yeah, you may feel it's not necessary because already have exciter directly influence the current, and current will give you an EQ. So what I'm going to control is not the internal generator. I have never concern of internal voltage of the generator. I have concern on a location far from my generator. Then just make a RC and IC be both negative. You're going to control remote location. So if you take RC, IC both negative, you're going to control a location outside of generator, depending on how large the RC and IC are. Okay, the larger, the further you can control a point. So how do I do that exactly? So this bottom figure does show the circuit connection. You see, on the terminal, I use PT to measure voltage, CT to measure current. I gave both to, there could be some control logic, or could be some circuit. You can actually adjust that RC or IC, then generate another voltage signal going to this voltage regulator. Okay, so how do I set up that RC IC? So assume beyond the terminal of generator, and on the right, there will be the power system. The generator is connected first through a step-up transformer, and then go through a high voltage bus and some other high voltage bus, maybe delivered over long distance. There's some location which can be the voltage or weak point. That's what I really want to control. Then you just need to estimate the total impedance from the terminal to that point. Then based on the R and this X, and you implement that value here. Then when you control the exciter, it doesn't control the terminal of generator, it's actually control that remote location. Okay, is that clear? Does that make sense? That's okay. That's why sometimes we need this load compensator. So now we have the entire the control block of the system. Okay, we draw them together. Here is one example, which is attribute type DC2A excitation system. This one is closest to what we have discussed. There are other type of excitation systems. Some are different. Why this one is closer for a control system? Because the exciter is based on a DC generator. Okay, so this is design of the exciter itself. Because exciter is going to provide DC circuit. So the question will be how can you generate that DC circuit? It has to be generated from another generator, and that generator has to be DC generator. Okay, so this is just a DC generator. So DC generator, the output terminal voltage of DC generator is actually the field voltage of the signal generator. And the input signal, which is the field voltage of the DC generator, is actually receive the control signal from your regulator. Okay, and here also tell you what this KE is for this case. The KE is actually the gain for the exciter, right? This is actually the KE, and there's also a tau E, which is time constant of exciter. We mentioned that one is very small. I think where here. So KE is actually depend on the design of the exciter as a DC generator, and the tau E is actually the like time constant of the DC generator. Okay, similarly to the tau G, which is the total time constant of the signal generator. So which means this is also another generator, DC generator, and similar to our bigger signal generator. This is very traditional design, but today's most of the exciters, they don't have to use DC generator to generate that DC circuit. They can use power electronics, or they can even take part of the terminal voltage to become this field voltage, but that will give you more complex design. That will make the model be slightly different. Going to this detailed control block. So this is a voltage transducer to measure the voltage signal. It will go through some block. And here, this is basically the amplifier, right? This is the time constant of the DC generator, DC exciter. This part is to model the saturation of the DC exciter. Okay, if you ignore saturation, so this one will be 1, and this one will be 1. Otherwise, it will be less than 1. KE is actually some gain of the DC generator, so that one is depend on this one. All right, so there are some other limit. So this is like a under excitation limiter. So you can model here. You can add the input here to limit the output. So that output will now be lower than this this limit. Oh, this is stabilizer. Okay. So this just gave you the data, because this is from a real model of a generator. Okay, from this table it's very small, but Ka is 50. The K is 50. Take a very large value. Okay, so we finish the part of the generators. The next part we'll quickly talk about other voltage control equipment. There are two categories. The first category is passive. The second is active. The passive means it's just designed to be a permanent part of the system. You can switch in and off, but that switching is not automatically. It can be manually. Even it can be done remotely, but you cannot use such equipment for automatic control. The examples basically will be writer, capacitor in either shunt or series connection. So there will be a full combination. The first one will be a shunt writer. The shunt writer will absorb excessive VAR from the system. So if you do have like over voltage issue, you need to switch in this shunt writer. That will limit the voltage. Usually the shunt writer is needed for open circuit or light load condition for long transmission line. So later I have a slide to explain why we need shunt writer for high voltage long transmission line under the light load condition. A series writer actually is not a voltage control device. It will consume some rated power, but main purpose of a series writer is just to increase the impedance of a path if you want to limit the current. So usually it's applied in fault current limiter. So if you detect a fault, you can switch in this series writer, so that will increase the impedance and current will be limited. But this series writer is not a device for voltage control. The next two can provide voltage control, which are shunt capacitors and series capacitors. Shunt capacitor will, if it switch in, it will provide rated power to the system, so it will increase voltage. Series capacitor is a VAR source. It can increase the rated power. It also decrease the impedance of transmission paths. We'll talk about series capacitor later. Second category is active. By active, which means you can include such a equipment into an automatic control system. The one example will be an on-load type changing transformer. So you can automatically adjust the type location to regulate the secondary voltage of the transformer. Similar condensers, static VAR systems such as SVC or Staycom, which are usually considered types of the FACS of flexible AC transmission system. Shunt capacitor is very simple. It just connected to any location you need some rated power. It may be far from a generation, so generation cannot provide rated power. So you want to switch in when the voltage is low. Once you switch in the shunt capacitor, it will increase the voltage at this point. It is not an active control device, but it can regulate normally the daily fluctuation of the voltage caused by load change. The location will be in either transmission system or distribution system. So in the transmission system, it will be at some substation to support the rated power to maintain voltage, especially during the highway load condition. If it's in the distribution system, it need to be close to large customers. It can help to correct a power factor. So if there's some industry load running a large motor, the power factor can be very low. So you can usually they need to have the capacitor there to provide the rated power to change the power factor. Disadvantage of the shunt capacitor will be even if it can be considered the source of VAR, but the value of the VAR depends on the voltage as a quadratic function. Okay, because the capacitor itself is basically still impedance, relative reactance. And if that relative reactance is constant, the Q will depend on the voltage magnitude squared divided by that reactance. So when you purchase this shunt capacitor, it is priced based on the capacity of Q. But once you install this shunt capacitor, it doesn't really give you that much of Q. Okay. For instance, if you want to buy a 25 MVAR shunt capacitor, okay, you pay the price for 25 MVAR shunt capacitor, and it is operated at 115 kV. But if your system at that location is exactly 115 kV, you don't need it at all. If you connect it, it will make a voltage higher. what you really need this capacitor is when your voltage is lower than that voltage. For example, like 109 kV, which is 0.95 per unit. And then you plug in this 0.95 per unit into this formula, you only get 22.5 MW. You always get less than what you purchased because it's not active control, right? It only just give you something more, okay? But how much you get really depends on system condition. So you only end up with only 90% of Q you purchased. Series capacitor. Series capacitor is also provide you Q calculated based on the readings. But for this case, if you add a series capacitor in the middle of transmission line, it doesn't depend on the voltage on either side. It depends on the current. So that gave a series capacitor some advantage, which is called self-regulating feature. One purpose of the series capacitor is just to mitigate the impedance of a long transmission, because most of any transmission line will have eventually will be more inductive. So when you add this capacitive readings in the middle, it will cancel some inductive readings. Which means you can deliver more active power, right? Remembering the formula, P is equal to ES, ER, S, and sine delta. This is active power delivered. So if you add a capacitor, it will just make the total reading smaller. Then P will increase, even the angle is same. So the advantage is self-regulating because the ready power depends on the current, not the voltage. The Q is equal to the readings multiplied by the current square. So if the system is operating under a heavily load condition, for instance, the bus B connected to a load and the voltage become worse and the current is increased, and the increased current will make more Q go into this substation B. Okay, that's different from the shunt capacitor. The shunt capacitor will have the Q proportional to the voltage square, but this one will be proportional to the current square. So under the heavily loaded condition, the voltage decrease, but current actually increase. So series capacitor will give you more Q compared to the shunt capacitor. But disadvantage will be whenever you connect inductance with capacitance, that will generate a resonance circuit. The inductance will resonate with the capacitance. Okay, for instance, you have this inductive readings and connected to a capacitive readings in series along the transmission path. So you are going to generate a resonating circuit, and this circuit will generate this resonance frequency based on the formula. So L will be the total inductance along transmission path. C will be total capacity of the transmission path. If you want to use the impedance of the line and the impedance of the capacitor, so we can also use this formula. So F0 is 60 Hertz. So if we compensate 10% of the transmission line, you are going to generate 19 Hertz sub-signal oscillation. Okay. This become a more significant issues, especially for the wind farms, because wind farm usually is built far from any city, where you have a lot of a very rich wind resource. But when you want to deliver the power, you have to build a long transmission path, and the long transmission path will, because the total readings will limit how much power you can deliver safely. So you want to always add some compensator, but this compensator will cost this subsignal oscillation. Even you just compensate 10% of the radiance, you will generate 19 Hz oscillation. So you also need to design some controller to mitigate this subsignal oscillation. Or you can detect the oscillation. If this oscillation is detected, you want to switch off this capacitor. All right, sorry, so it's a little bit over time. We have a few slides left, and we can finish on Thursday.